Now in this article, theory of interference bands, what we have to do first? We have to find expression for part difference. So part difference is given by y into d upon d. Y is the distance of point of observation on the screen from its center. D is the distance between the two coherent sources, and d is the distance between the plane of the two coherent sources and the screen of observation. Second one, we have fixed the position of nth breadband So it is given by yn b for bright, and it is given by n into lambda into capital D upon small d. Position of nth dark band. So number is same, therefore yn, but it is for dark band, so I will add the suffix d for dark, b for bright. So this is equal to n minus half lambda capital D upon small d. In this case, in the first case, n is equal to 0, 1, 2, 3, 4, dot, dot, etc. In this case, n start from 1, 2, 3, 4, 5, etc. ये डार्क बैंड के नंबर 1 स्टार्ट होता आणि ब्राइट बँड के नंबर 0 स्टार्ट होता. 0 नंबरची ब्राइट बँड असेल त्याला सेंट्रल ब्राइट बँड म्हणतात. We observe alternate bright and dark band, so their numbering is like this. Now, third, these two parts we have already seen. Now, third part that we are going to see is the expression for bandwidth. The bandwidth is denoted by bandwidth, or it is also called as a bandwidth. It is denoted by either beta or width for W. Like this. तो हा फॉर्म्युला आता आपल्याला डिराइव करायचा आहे. थर्ड पार्ट like this. So first we will define what is meant by bandwidth, and then we will derive its expression. Actually, in this equation, this part is the bandwidth. This part is the bandwidth. For bright and dark band, the expression for the bandwidth will be same. So we will define the bandwidth. Definition of bandwidth. It is the width of the band. So now we know the nature of the interference pattern. Suppose this is a dark band, bright band, dark band. Alternate dark and bright bands are observed like this. So the distance between the center of the bright band and next center of the bright band, this distance is called as the bandwidth beta. The distance between the center of the two successive dark band, it is also called as a bandwidth, like this. So this bandwidth is measured also in this method. Starting point of the first dark band, starting point of the second dark band, same. So definition of bandwidth beta is similar to the wavelength lambda. आपण वेवलेंथची डेफिनेशन ट्रान्सवर्स लॉन्जिट्युडिनल वेव्हसाठी दिलेली. For transverse wave, It is the distance between the two successive crust or two successive troughs. इथे पण तसंच येते. The distance between the two successive bright band or two successive dark band is called as a bandwidth. So wavelength definition आणि bandwidth definition सारखे येईल. So definition of bandwidth beta. The distance between two successive two consecutive bright band or dark band is called a bandwidth. Is called a bandwidth. Now we have to derive the expression for this. Expression for bandwidth. Beta. First method. Method 1. Using conditions or using the positions of bright band. Using conditions for bright band. So suppose this is a screen where the interference pattern is observed. This is the center of the screen, say O dash. This is the point P1. This is the point P2. So at point P2, at point P1, two successive bright bands are observed. So if this band has number 9, then it will be 10. 9, 10, 1, 2, 49, 50, 73, 74. If this band has number n, then this band will have number n plus 1. So distance of the n bright band is yn, and it is given by this formula. And distance of the n plus 1 bright band, it is yn plus 1, like this. So the distance between the two successive bright band is P1, P2, and this distance is called as beta. So we have to find beta like this. Beta, or it is denoted by W. So now using this formula, let yn is equal to distance of nth bright band at point P1, distance of the n bright band from center O dash of interference pattern. आपल्या फिगर मधलंच आपण पॉइंट घेतले interference pattern. Therefore yn is equal to हा फॉर्म्युला वापरून जातो n number of the band into lambda capital D upon small d. This is equation 1. Lambda is a wavelength of the monochromatic light. Like this. Similarly, yn plus 1 is equal to distance of distance of n plus 1th bright band from at point P2 from center O dash of the pattern. Therefore, yn plus 1 again same process. Band the number first बदलेल n plus 1 into lambda into capital D upon small d. This is equation second. So by definition, therefore bandwidth beta is equal to distance of the n plus 1 bright band minus distance of the n bright band. So this is equation 3. Therefore put 1 and 2 in equation 3. So we get bandwidth beta is equal to n plus 1 into lambda capital D upon small d minus n into lambda into capital D upon small d, and therefore this is equal to n plus 1 minus n bracket complete lambda capital D upon small d common, and that is equal to 1 into lambda into capital D upon small d. And therefore beta is equal to lambda capital D upon small d. So this is the expression for the bandwidth using the condition of the bright band. So this is the equation capital E. This is equation capital E. Like this. Second method. Method 2. Using condition of dark band. Let nth and n plus 1 dark band are observed at point P1 and P2. Let nth and n plus 1 dark bands are observed at points P1 and P2 at distances yn and yn plus 1 from center O dash respectively. Then yn is equal to distance of the n bright band n minus half lambda capital D upon small d. Equation small. Distance of the nth dark band is equal to n plus 1 minus 1 half lambda capital D upon small d, so that is equal to n plus half lambda capital D upon small d, this is equal to B. So bandwidth beta or W is equal to by n plus 1 distance of the nth direct band by n distance of the nth direct band. These are the two successive direct band, 7 and 8, 49 and 50, 72 and 73. So distance between the two successive direct band is called as the bandwidth. This is equation C. So put A and B in C, and therefore bandwidth beta is equal to n plus half lambda capital D upon small d, n minus half lambda capital D upon small d. So this is equal to n plus half minus n minus minus plus 1 half, and common factor is lambda d upon d. So n will get cancelled, and therefore this is equal to 1 into lambda into capital D upon small d. Therefore the bandwidth beta is equal to lambda capital D upon small d. This is equation capital B. So see these two equations. Expression for bandwidth using condition of brightness, expression for bandwidth using condition of darkness. So see the right hand side of equation A and B. Lambda capital D upon small d, lambda capital D upon small d. So equation A and B are same. याचा conclusion काय काढता येईल आपल्याला? Bright and dark band, distance between the two successive bright band and distance between the two successive dark band in an interference pattern are equal, means bright and dark bands are equally spaced now. They are equidistant from each other. So this is the important conclusion. Since equation A and B are same, hence in an interference pattern whatever may be the experiment, bright and dark band are equally spaced, equally separated from each other, or bright and dark bands are equidistant from each other, So this is the important conclusion. Same conclusion we have given in stationary wave. Nodes and antinodes are equally spaced. Waxing and waning are equally spaced by time. This is a time factor also. So in the conclusion of nature of interference pattern, we have given one conclusion. In an interference pattern, the bright and dark bands are equally spaced, very close to each other, and they are parallel to each other. Now, why they are equally spaced, we have proved by equation A and B. Okay, and now why the bands are close to each other? See this equation: beta is equal to lambda into capital D upon small d. So beta is directly proportional to lambda. So lambda is very small for visible light. It is from 3000 angstrom to 8000 angstrom. So since lambda is small, therefore bandwidth is also small. Also, lambda is very small in nanometer. Therefore, beta is also small. Therefore, bands are very close, equidistance, and parallel to each other. Parallel to each other. So we have given this conclusion, but it is proved by knowing this expression for the bandwidth. So bandwidth is the one of the important characteristics of the interference pattern like this. So there are two types of equations for bandwidth. Equation A using the condition of brightness. So this figure is common for both the method. At point P1 and P2, we are assuming the two successive bright band having number n and n plus 1. So distance between P1 and P2 is equal to beta, equation 3. Bandwidth is the distance between the two successive bright band n and n plus 1 are the number. So yn is given by this relation, number of the band multiplied by lambda capital D upon small d. So 1 and 2 give the distances of the nth and n plus 1 bright band from the center O dash. So by subtracting these two equations, we get the bandwidth lambda capital D upon small d. Lambda is the wavelength of the monochromatic light used. D is the distance between the plane of the coherent sources and screen for observation, and small d is the distance between the two coherent sources. Same formula is derived by assuming the two successive dark band observed at point P1 and P2. So again P1 P2 is equal to beta, and this beta is having same formula. So distance between two successive bright band, equation A, and distance between two successive dark band, equation B. A and B are same, therefore we can get this conclusion like this. So bright and dark bands are equally spaced from each other. Since lambda wavelength is very small in nanometer, therefore beta is also very small. So bands are close to each other, they are equidistant from each other. This is the last conclusion. They are close to each other like this. They are equidistant from each other and they are parallel to each other. So nature of the interference band is confirmed by these mathematical equations. Now in the theory of interference bands, we know the value of path difference at any point on the observation screen. Then we have seen what are the positions of bright and dark band, how the positions are located by using those relations. Then we have seen the important characteristic of the interference pattern, that is the bandwidth. Bandwidth is given by lambda capital D upon small d. So it depends upon the two distances capital D and small d, and it depends upon the wavelength of the light used. Then bright and dark bands are equally spaced from each other. That is also one point. Now, next we have to see the distribution of intensity of light. आपण स्टेशनरी वेव्हच्या फॉर्मेशनमध्ये सुद्धा हेच बघितलं होतं. ॲट अँटीनोड द अँप्लिट्यूड इज मॅक्झिमम, इंटेन्सिटी इज मॅक्झिमम. ॲट नोड इट इज मिनिमम मे बी 0. फेनॉमेना ऑफ बीटमध्ये पण तसंच बघितलं होतं. वॅक्सिंग आर हर्ड ॲट सर्टन टाइम. मॅक्झिमम इंटेन्सिटी ऑफ साऊंड इज कॉल्ड एज द वॅक्सिंग. मिनिमम इंटेन्सिटी कॉल्ड एज द वॅनिंग. सो अल्टरनेट वॅक्सिंग अँड वॅनिंग आर हर्ड. Maximum minimum intensity. So intensity of sound is distributed waxing waning like this. In the formation of stationary wave, the amplitude is distributed between maximum minimum at antinode, node, etc. इथे पण तसंच आपल्याला बघायचं. तर इंटेन्सिटी ब्राईट बँडला नक्कीच मॅक्झिमम आहे, पण ती किती असेल आणि ती कुठल्या कुठल्या फॅक्टरवर डिपेंड आहे ते आपल्याला बघायचं. सो वी आर कन्सिडरिंग द इंटरफरन्स ऑफ द टू waves having same amplitude. आपण आयडेंटिकल वेव्ह coherent sources use करतो आपण. So they are having constant phase difference. That phase difference phi, we know that the phase difference phi may be 0, greater than 0, or maybe or less than equal to 360 degree. So phi is a phase difference between the two waves from the coherent sources. So now if phi is the phase difference between the two coherent sources, then what is the intensity distribution in the interference group, that we have to see. So we are considering the two interfering waves interfering each other from two coherent sources S1 S2 at point P. Let E1 E2 are the electric fields of the two waves interfering at point P. E1 is equal to E1 0 into sin of omega t. So this is equal to E0 sin of omega t. This is equation 1. E2 is equal to E2 0 sin of omega t plus phi. Phi is a phase difference, so that is equal to E0 sin of omega t plus phi. This is equation 6. E1 0 is equal to E2 0 is equal to E0 is equal to amplitude of each interfering wave. E1 0 is equal to E2 0 is equal to E0 is equal to amplitude of each interfering wave. Phi is equal to phase difference. This factor is important. Phi is equal to phase difference between two waves at point of crossing P, like this. So the two waves have equal amplitude. If I0 is equal to intensity of each interfering wave, then we know this property. For any type of wave, intensity is directly proportional to the square of amplitude, and therefore I0 is directly proportional to E0 square. Say this is equation 1. आता ह्या दोघे वेव्ह क्रॉस झाल्यानंतर रिझल्टंट वेव्हची इंटेन्सिटी आपल्याला काय असेल ती आपल्याला काढायची. प्रिन्सिपल ऑफ सुपरपोजिशन ऑफ वेव्हचा आपण करणार. तर कॉम्पोजिशन ऑफ टू एसएचएमची थिअरी आपण एसएचएमच्या ऑसिलेशनच्या चॅप्टरमध्ये बघितलेली, ती इथे आपल्याला यूज करता येऊ शकेल. लेट E is equal to amplitude of electric field of a resultant wave resultant wave at point P, then by the principle of superposition of waves, it is applicable for sound waves, light waves, etc. So E is equal to E1 plus E2. This is equation, this is equation E. This is equation 3. So actually we have given this principle like this. Resultant displacement is a vector sum of individual displacement. Y is equal to y1 plus y2. तो y is equal to y1 plus y2 जाके अपन के E is equal to E1 plus E2 घेतला. E1 E2 च्या व्हॅल्यू फक्त सबस्टिट्यूट करा. So using 1 and 2 in 3, put 1 and 2 in equation 3. So E is equal to E0 sin of omega t plus E0 sin of omega t plus phi, and therefore E is equal to E0 into bracket sin of omega t plus sin of omega t plus phi. So here you can use the trigonometry. Sin of A plus sin of B is equal to 2 times sin of A plus B by 2 into cos of A minus B by 2. So we know this simple trigonometry. Sin of A plus B is equal to 2 times sin of A plus B by 2, etc. So using this formula here, so this is A omega t म्हणजे A झाला, omega t plus phi म्हणजे B झाला. So if you use this trigonometry, then E is equal to E0 into 2 into sin of A plus B means omega t plus omega t plus phi by 2 into cos of A minus B. So omega t minus omega t minus phi by 2. So this is equal to E0 2 times cos of minus phi by 2 of the lumina into sin of 2 times omega t omega t plus phi by 2. और 2 दोघांना डिवाइड केलं म्हणजे ओमेगा टी 2 टाइम ओमेगा टी बाय 2 एकच ओमेगा राहिला प्लस पाय बाय 2. सो दिस इज इक्वल टू इक्वेशन 4. नाउ दिस पार्ट इज the amplitude of the resultant wave. In equation 4, 2 times E0 cos of phi by 2, cos of phi by 2 is equal to cos of phi minus sin कट झाला. 2 times E0 cos of phi by 2 is equal to amplitude of a resultant wave. Therefore, if I is equal to intensity of the resultant wave, then intensity I directly proportional to the square of amplitude of the resultant wave, and that is equal to 2 times E0 cos of phi by 2. So I directly proportional to 4 times E0 square cos square phi by 2. This is equation 5. So this is equation B. So when the two waves, they are not identical because they are having phase difference like this. So they are having equal amplitude, equal frequency, etc. So equation B gives the intensity of the resultant wave at the point of crossing, and equation 1 gives the intensity of each wave at the point of crossing. So resultant intensity and individual intensity, you can take the ratio. So B by A gives I resultant intensity upon I0, intensity of each wave is equal to 4 times E0 cos square pi by 2 upon E0 square. Proportionality constant cancel only. So I is equal to I0 into 4 times cos square pi by 2. This is equation C. So equation C gives the expression for the intensity at a point of crossing where the two waves differ in phase by phi. Phi is a phase difference. So this is a important conclusion. Equation 4 gives, equation C gives equation C gives intensity of resultant wave at a point P where two interfering waves differ by phase angle phi. The phi one mainly depends. I depends on phi. So complete phenomena of interference is depending upon the phase. Same phase crossing we get constructive interference. Out of phase crossing we get destructive interference. So that conclusion, same phase crossing gives the constructive interference maximum intensity. Out of phase 180 degree phase difference produces the destructive interference minimum intensity. That can also be proved mathematically by this relation. आता ह्या इक्वेशनचे आपण स्पेशल केसेस बघणार आहोत. फेज डिफरन्सचे व्हॅल्यू फक्त आपल्याला चेंज करायचे आहेत. नाउ वी टू सी द डिफरंट केसेस. केस नंबर 1. When E10 is equal to E20 is equal to E0 and phase difference phi is equal to 0 degree or 360 degree, that is 2 pi radian. Therefore cos of phi is equal to 1, cos square phi is equal to cos square phi by 2 is equal to 1. Actually this is cos of phi is equal to cos of 0 is equal to 1. Cos of phi by 2 is equal to cos of 2 pi by 2, that is equal to cos of pi is equal to minus 1. So for both the cases cos square pi by 2 is equal to 1. Therefore equation C gives I is equal to 4 times I0. This is result 1. So this is called constructive interference. Second case, when the amplitude are equal, E1 0 is equal to E2 0 is equal to E0 and phase difference phi is equal to 180 degree, then I by 2 is equal to 90 degree, cos of phi by 2 is equal to cos of 90 degree is equal to 0. Therefore, equation C gives I is equal to 0. This is equation second. This is called destructive interference. This is called destructive interference. Like this. Now, what is the importance of this case? Here, bright band are full bright and having maximum intensity intensity 4 times I0, while dark bands are completely dark having zero intensity. This having zero intensity. Thus, intensity difference between bright and dark band intensity difference between the bright and dark band is maximum and therefore there is a good intensity contrast and the interference bands have good intensity contrast. So for good intensity contrast, this is the condition. When the two waves have equal amplitude, the intensity contrast is good, like this. So two interfering waves of equal amplitude or intensity have good contrast of intensity. This is one of the necessary conditions for steady interference pattern. Now, case number C. When the amplitudes are not equal, E1 0 is not equal to E2 0, then The intensity contrast is poor. The intensity contrast is poor. So good intensity contrast is required, and it is possible when the two waves have equal amplitude, like this. So this theory is similar to the theory of composition of two SHM, where the two waves have same frequency, same period, and having certain phase difference between them. Okay, we will stop here.